Hello and welcome to the next part of this beginner's tutorial series on how to do your first DirectX 12 application in C++ from scratch. During the last episode, we uploaded and bound our newly created constant buffer to our graphics pipeline. The buffer contains the path data, which is basically a struct that holds our view projection matrix. We will use that to do 3D drawings. In this episode, we have planned to create a 3D box and upload it to the GPU, and then we will probably do some depth buffering. I may do that in a separate video depending on how long this will take. So I've looked into different algorithms to create a box. Usually I use an index buffer, which reduces the amount of vertices needed in terms of drawing the box. Since we haven't implemented an index buffer yet, and we might not even in this episode, since it's fairly simple, you would simply create it like you would create a vertex buffer, and you would use that to do instance drawing, or rather index drawing, instead of iterating over every vertex. But yeah, maybe we will do that in the last video, implement a index buffer and upload every data point to our GPU. Since we would like to kind of like, yeah, well, clean up this code. Anyway, let us start out by defining what we're trying to do. We're trying to create a cube, 3D cube, that will have 6 faces that can be thought of sort of like this. And each face will consist of a triangle, so we need to define these faces and triangles by specifying their in total 6 vertices each. If you do instance buffering, or rather drawing, you can reduce the amount of vertices, then one face only takes 4 vertices. But we won't bother with that, and we will go through the rather long-winded approach of actually creating all the vertices without indexes. So let's start up by defining which planes these faces will be aligned to. We will do something that is axis aligned, so it's not rotated yet. We can always do that later on. Yeah. But let's look at our camera. Our camera is at the negative C position, a bit raised on the y-axis, and it's looking at the origin. So if we were to find the face that we are looking directly at, it's defined in the y and x plane. So let's start out by creating the y-x plane face. So we need something that is we need a triangle that is drawn from the low y position and the if we imagine our coordinate system here, sorry, going through down through here, we can imagine that this is a negative y value and a negative x value. It will also, in the 3D space on the C-plane, actually be a negative value. So let's start out by defining our vertices here. We will simply do a vertex array here. Which will hold for now 16, but we will probably increase that. Let's set our first one to the negative x position of 1, the negative y position of 1, and the negative z position of 1. So this is the box plane. No, I don't think so. You can. But my connection is 320 megabits or yeah, megabit per second. No, I won't show your OBS settings on the stream. I'm sorry, man. But I set the bitrate to 4,200 kilobits per second. For full HD. I'll just type it in the chat. I don't know. No problem, man. Anyway, so we were defining our vertices here. So we want the face facing our camera, our face facing our camera here, to be defined by the 3 negative coordinates here. And then the next vertex will be this one, so it will be positive on the y, but otherwise it will be similar. Then we want to draw this one, since we're doing clockwise drawing. Let's see. That's the next vertex. So that will be positive on the x, negative on the y, and negative on the z. Then we will start drawing this one. We will start up here. which will be basically the same as this one. It will have a positive y, but still a negative x and c. We will create the one with a positive y and sure thing, man. I'm just not really answering generalized stream questions because I'm recording a video for YouTube. So, and I can't help you debug your OBS problems. All right, so the next position is up here where the x is positive, the y is positive, and the c is negative. And then we do the last vertex, which is exactly the same as this one, where the x is positive, the y is negative, and um, the what do you call it? Yeah, you get the idea. All right, right now we have 6 vertices. We can keep it as is. Instead, we want to upload this data here. So we will give it a pointer to that array. We will right now upload 6 vertices. And our color is defined to be black. Let's do a default color of green so that we don't need to specify it, but yeah, well, maybe we want to specify it. Let's see. This is the green color. Yeah, let's just do it in case we need debugging. Let's see. And the other part of the face here. Whoops. Let's swap that so that the ordering is all right. All right. Let's do this. It will probably look weird. Yeah. It actually doesn't show anything. That's because we have changed our underlying data structure. Let's see if it actually gets uploaded correctly though. And let's see, we want to sort it by these parameters. Well, we do have one. Let's do indices. We do have 6 vertices. All right. So right now we upload the vertices correctly. We do not draw them correctly since we right now only try to draw 3 vertices. Let's increase it to 6. It probably doesn't still show anything because the coordinates are now in world space coordinates. They are no longer mapped to screen space coordinates. So that means that we actually need to do some translations here. One quick note in terms of constant buffers and DirectX and DirectX math library. The matrices that are created with the DirectX math library are row major, and the shader language expects column major data ordering, which means that you have to flip your vector times matrix multiplications. It's just the way that the math library is built. I've done something else during my own project because And there are a few optimizations of doing column matrix ordering, but that might be a reason why you need to um, flip certain multiplications here. But the shader language has a method for multiplying um, uh, vertices slash vectors with matrices. And remember, this is what needs to be ordered in a different order if you have column major ordering. Let's see. And this needs to be, of course, a float 4 where you add this 0, 1 because a 4x4 matrix can only be multiplied by a vector of 4 numbers. And since you don't want to discard the last matrix by vector multiplication, since it contains the so-called translation, you add a 1 to your position vector. All right, let's see if this changes anything. Right now you can see we actually have a primitive. So it worked. You might be asking, why does it look like that? Well, that is because of our camera position. So if we inside our, let's disable this code, we don't need it anymore. If, excuse me, we change our camera position not to be elevated, but looking directly at the face we just defined, we will see a square. So the higher we go, the more skewed the view on the plane will be. As you can see here, it's like we are looking at it from a different angle. Right now, there's no depth handling, so things might look weird. But we successfully defined this entire plane here. We could now do the next plane, which is going to be behind this. So let's define this 6, 7, 8, 9, and 10, 11 here. And we still have space, and we will double the amount of vertices. But we will change the color here so that this face is red instead. And we will, since we're doing the other plane, we should actually flip the ordering a bit, because we're basically drawing this one, which is on the other side. It will hold the positive C value for all vertices, and we should look into the ordering of them. Let's see, did I miss anyone? Nope. Okay, so since this point is actually the one that corresponds to this point here, but only with a positive C value, we can actually calculate that the first vertex is the one that we specified as the second one here. So let's flip those. It's the one that has a positive Y, a negative X, and now a positive C. So this is the first one. And let's move this. So our next vertex here will be the one that corresponds to this one. So it will have a negative x, a negative y, and a positive c. So that simply fits. And then the last vertex will be this one, which actually corresponds to this one now. So it will have a positive y, a positive x, and a positive c. All right, great stuff. Our next vertex here will be the one that corresponds to this one. So it will have a negative x, a negative y, and a positive c. Then we will draw this one, which will be the one with the negative y, the positive x, and the positive c. Then we will draw this one, which will be this one. So it will have a positive y, a positive c, and a positive x. All right, let's try doing this, but we change the color. Right now we won't be seeing anything. And did we mess up anything here? Let's see. Oh yeah, we are actually not drawing the vertices themselves. That's why. And things might look really weird because we have no sense of depth right now. As you can see here, everything just gets overwritten. But we do have the sense of a plane that is actually extending backwards. All right, that's the two faces here. Yeah. Maybe we should do the two sides. Yeah, we could do that. Once we have made a practice in terms of doing these things, they well, they do get yeah, we generate them fairly quickly. But I actually think that the whole perspective thing is rather confusing. So even though we are generating vertices, the missing sense of depth means that things end up looking rather confusing. So we should probably set up the depth buffer here. Okay, a depth buffer is a buffer that controls how far into the 2D screen space things are supposed to be rendered, and it discards pixels that are obscured by other pixels, basically. So yeah, we will create the depth buffer. And it will actually be a different kind of buffer. So we need to do changes to our resources here. We would like to be able to initialize as depth buffer. We of course still need our device, but we want to be able to specify a width and a height. So let's create that method. We can reuse our heap properties. This will be created on the default heap. The GPU will be doing the writing to it. We will not be using the CPU to write to it, so we don't care that it's created out of reach for the CPU. We will create a texture. Since the depth buffer is a texture that for each pixel gets filled with a depth value that tracks whether a future pixel is allowed to overwrite the current pixel. So we need to define the dimension, which is a texture 2D. And the alignment will be our standard alignment. I think it's a minimum of 16 kilobytes. And we will specify the width as our width, the height as our height. And since we do not have a 3D texture, we will only have an array size of 1. This will contain no MIP levels because we do not have scaled versions of the depth stencil texture. The format will be simply double precision. Now we will store single values as a depth value. So let's see, DXGI format. Do we have something? Yeah. This is a type that is used for depth buffering. So D32 is actually an appropriate format for this kind of buffer. We will initialize our sample this and we will not be using sampling, so we don't care. Then we need our resource layout, which is a texture that has an unknown type, and then we need to initialize with some flags. And flag allow depth stencil. Well, then we need to create our committed resource. Yeah, so we will do exactly as we did up here. We will create a committed resource. We will specify the heap properties. We will specify the resource description. And we will specify a resource state. And let's see. We have some depth right, I think. That sounds appropriate. We would like to write depth information to it at the standard, and then we, oh, did I specify something wrong here? Heap flags, okay. Yeah, I missed that. D3D heap flags none. And then, yeah, okay. And then the last component is a clear value. And it's a struct clear value that will be initialized as 0. And let's see, what does it contain? It contains some information about the depth stencil. It also contains a format. Remember, our format is specified right up here. Then we want some clear value information in terms of the depth stencil. Well, it's especially the depth. And the depth is a clear value of 1. Remember, DirectX scales depth values between 0 and 1. And I actually think that 0 is the one that is closest to the camera. If I do not recall incorrectly. Let's see, let's set the stencil to 0. meaning that we will not be doing any stenciling. And then we give it the, does it want the address? Yeah, it wants the address. And that's it, nothing else. And then we need to error creating depth buffer. Let's see, too few arguments in function call. We need heap properties, heap flags, the resource description, initial resource state. Oh, okay, we of course need to specify where to store it. We forgot the old IID, PPP. All right. So now we actually can create a resource on our renderer API. We will store it up here since it's basically related to our pipeline. Depth buffer, and we will initialize it after we initialize our pipeline. Initialize as depth buffer, and we will pass in our device pointer. We will pass in our width and our height. And well, that creates our depth buffer. Since it's located on the GPU needs to know where to find it. We need a descriptor heap to contain the information about the depth buffer itself. We will create a small wrapper here inside a folder called the descriptors, and we will create a wrapper for that. Descriptor heap. It will be really simple, but since our renderer API would like to store it, we will create one. Let's see, engine here, and of course we want to include that here, and then we will create a wrapper as per always, since this is a DirectX interface. Descriptor heap, and we will create an empty constructor that is defaulted. We will create a destructor, and we will create a release function. And we will, as per always, do the get and then reset here. We will do the release function on destruction, and we will allow our render API to store one of these. Let's see, we will move these since they are pipeline essentials, and we will include a descriptor heap. I actually think, oh, I didn't really name it correctly. Let's rename it to D12. And inside the class itself, D12. There we go. And of course, like this. All right. We will of course need some functionality. Let me just close some of this. Of course, we need to update that as well. Depth heap disk heap, and we will need a initialize function. That will take a ID 3D12 device because it probably needs a device to initialize it. Let's see. Whoops. And we will simply try out, can we create a descriptor heap? Yeah, we can. What do we need? We need a descriptor heap description. And then we need somewhere to store it. So the 3D12 descriptor heap description, we will store that initialized as 0. And we will pass that in. And we will, of course, pass it our com pointer here. And we will wrap this in our YouTube eval h result. And error creating descriptor heap. Let's see, we missed a parenthesis here and want to create it like that, right? Did we miss one more? Yeah, we did. Okay. And let's see. Our descriptor heap here is supposed to contain a number of descriptors. Right now we will simply hard code maybe depth heap. Yeah, we will simply hard code it as a descriptor heap here. Okay, and the node mask is 0. And the flags are none. Does it need to be shader visible? I can't remember. I don't think so, but no, it doesn't need to be shared. It's output merger related, so I'm pretty sure that it doesn't need any flags. And lastly, we will set the type to a depth stencil heap. All right. And we will hard code it as a depth descriptor heap, initialize as a depth descriptor heap, and we will pass in our address of our device. Lastly, we need to actually create a description. So we will ask our device to create depth stencil view, and it needs a resource interface, which is our depth buffer here. Then it needs a depth stencil view description, d3d12 depth stencil view description, dsv desk, that is initialized as 0, and we will simply pass that in. DSV desk, does this create? No, it doesn't return an H result. And a descriptor handle, a CPU descriptor handle, meaning it's the start of where to place the descriptor itself. We will simply take our descriptor heap, which has a size of 1, and we will get the CPU address of the heap start, and we will make sure that this description gets stored there. Okay, we're almost done. can't I spell this correctly? Oh, capital D. Okay, we need to specify a format here, which we already have because we specified that in our actual resource initialization. We also need to specify a view dimension, meaning that we tell the system how to interpret this. Since we set it to a texture, we need to disable the MIP slices because there are no MIPs in this texture. And the flags are simply none. All right, let's see if everything compiles. Everything compiles. But we have not enabled depth buffering. So that's the last part we need to implement inside our pipeline. Right now we have created all the resources. We could use NVIDIA Insight to actually illustrate that we created the resources and bound them to our pipeline, but we will, we haven't bound them to our pipeline actually. But let's start out with actually enabling depth stenciling. We have currently disabled it. We want to enable it. We also need to set a format for our depth stencil, which is our format here. And we will compare each depth value with a less than function and of course write whenever we need to. Okay, let's see if everything still compiles. Let's see, we have a debug problem here. Okay. Okay, so we need to do something when we do our draw call. That is, of course, binding the whole thing to the actual draw calls and pipeline. It complains that we haven't done that yet. And I mentioned it earlier that that is entirely true. We need to grab the CPU address of the handle for the depth stencil view, and we will get our descriptor heap here, and we will simply get the address for the CPU start, since we only have, or rather the descriptor heap handle, since we only have one depth stencil view, and it's stored right at the start of the heap. Therefore, we simply can grab the heap and its starting location. No need to offset it. Okay. The thing is that the render target here can actually take a description, or rather a handle, to our depth stencil descriptor. That is. So we can pass it that value. We would like to see if this sorts our error. It sorts our error. Right now we have a black screen though. So the problem is that we actually need to clear the depth stencil as well between every frame. So let's see. We usually do it while we clear the render target, and it's a graphics command call. Clear depth stencil view, and we need to pass it our handle here, DSV handle, the clear flags, clear flag depth. Then we want to clear it to a depth of 1, and we do not do any stenciling, we do not do any kind of rects, so therefore the last values will be disabled. And here we go. We now have a proper sense of depth. Right now, our front-facing plane here completely dominates the plane behind the actual one, which was to be expected because we actually defined these vertices here with a positive offset on the z-axis, meaning a forward-going direction, which means this is actually closer to our camera, which is placed on the negative z-axis. So therefore, everything looks quite all right. Let's try raising the camera a bit on the y-axis. And as you can see, we now have visibility of our two planes. Nothing is weirdly drawn. If we lower our camera a bit here, you will start to see the outline of a cube. So this is 3D rendering. What's left is actually defining the last vertices of this box. We will do one more side, as now we have better debugging of this. But what we need to do in this episode is basically wrapped up and good to go. We now have 3D rendering, and we might do the next video in terms of uploading the data and creating them on the actual default heap, since it's a performance optimization and resource management is part of DirectX, and it's a nice introduction to that topic. But let's try if we can define, maybe let's increase this to 18. Maybe let's do a macro, because then we don't have to box global box vertices 18 right now. Then we only need to change that value once. All right. Yeah, nothing will happen, I think. Yeah, it doesn't know, or it doesn't have any information about the vertices themselves, so they are basically skipped. But let's try defining the plane that's on the side here. In our diagram here, that would be this plane here. Let's start on defining this one. Let's see if this is our y and x plane. This will be our z and y plane. Let's see, y, z. So if we are supposed to draw the vertex that is farthest away from this plane here, we would basically draw the one that is down here. That would mean a negative y value, a negative x value. X will be negative for all the vertices here, and a positive c value. Let's see, let's define 3 vertices here. 12, 12, 13, 13, 14, 14. And we talked about this being negative x no matter what, so let's make sure that every position is negative x1, and then it's negative on the y, and then the c was positive. Then this will have a positive y, but still a positive c value. Then this will have a negative y, a negative c value. And we will draw this in a different color. We will use the blue ones for this. Let's try that. Okay, as you might see, we do have a plane there, but let's see, maybe we need to turn our camera a bit by offsetting it a bit to the left, maybe even more, so that we can see the plane that we're working on. All right, as you can see here, we have our side. We will define the next part of this. Whoops, 15, 15, 16, 16, 17, 17. All right, so we will start by creating the one with a positive y, a positive c, and of course a negative x. Then we will draw the one with a negative c, a positive y, and a negative x. Then we will draw the one with the negative y, a negative c, and a negative x. And let's add a bit of green to this. There we go. There we go. So that's the other side. And yeah, you get the basic idea. Now it's way more easy to kind of visualize where we are drawing the vertices. I'll leave it up to you to complete this on your own if you want to do this method. Index drawing is way easier, so you can actually only you can skip all the vertices for each of the 6 planes, and you can simply just define every corner of the box, the cube, and through indexing you can use those corners multiple times in terms of drawing the actual triangles. So it's way more efficient. You don't have to store as many vertices, and you can reference a lot of vertices multiple times, which is usually the thing you need for drawing polygons. Anyway, I think this is it for this episode. We've covered a lot of different topics. We've covered a lot of ground, and we have actually fully functional 3D rendering. Congratulations if you stuck around this long. If you found any of this helpful, entertaining, inspirational, or something else entirely, feel free to like, comment, subscribe, or even support the channel. I'll probably do one more episode in terms of the resource management, in terms of uploading to the heap and maybe creating an index buffer. But that is all I have planned for this series. If there are certain topics that several viewers would like me to go over in terms of doing drawing and stuff on DirectX 12, leave a comment or drop by when I'm doing live streaming. I'll take it into consideration, and if there's enough requests on a certain topic, I might allocate time to do it. All right, but thanks for watching. Stay strong, focused, healthy, and keep on trucking. Hopefully I'll see you around. Bye bye.